Okay, we're back in the gear making business. This is the index drive gear. It's one of a pair. This one's 21 tooth and I've got to make a 43 tooth. And the reason those are oddball numbers is because of the gear ratio of the Van Dorman head. Here it is, straight off the machine. Reference, this is 01. I'm going to stop that right here for a second. It's time to deliver an important message. I'm guessing you thought this was going to be another Tom Makes a Gear video. And it is. But at the point where I stopped the video to make this little PSA, the process failed. I was in the middle of making that 43 tooth gear, which I was confident that I should be able to make, when the machine exhibited what I can only call an extinction level vibration. We're talking about a vibration that was so violent that I could feel it through the floor of the shop. And the machine itself vibrated itself about 4 inches across the shop floor, thereby expressing its displeasure with whatever it was I was asking it to do. This was a surprise to me. And so this is what it looked like. I don't know if you can see that, but that's pretty cut up. There's no way I'm going to turn that into a gear, or at least not that size. So I had a big think about it, and I started to think about all the things that could cause that kind of vibration in terms of the structure of the machine, the layout, the setup of the hobbing parts of it. And I thought, okay, I'm just going to go through this and I'm going to look at everything. And I found something that I thought was it, wasn't it. Found something else that I thought was it, wasn't it. In fact, 6 times I thought I had found the problem. But I hadn't. I spent a better part of a week converting fairly expensive 01 tool steel into scrap for purposes of this gear. Now, I'll be able to reuse this stuff for something else, but that's not the point. I was so frustrated at the end of that I decided I had to set it aside and work on something else. And I built that turntable that is the subject of a couple of previous videos. But this really brought me around to the point where I was thinking quite a bit about failure, because I was frankly failing quite a bit. So I wanted to talk a little bit about that. You can call this a PSA, I guess. But I want to talk about failure and the role of failure in engineering. I read a good book about that long time ago. I think it was probably my freshman mechanical engineering class. And this was a role about what it means to fail and what benefit you can take in terms of the practice and art of engineering. And I think most of you know that I was a mechanical engineer during my real life before retirement. And I can tell you that I failed a lot. I was increasingly a taker of risks because in my experience, after the first couple of times when I had to deal with the consequences of failure, I realized that I could improve myself, improve my practice of engineering, improve my leadership, improve everything if I just paid attention to what had caused the problems, whether it's a failure of mind, a failure of judgment, a failure of calculation, a failure of whatever. I could figure out how to do it better, and I could do it better. And I got increasingly desensitized to the consequences of failure. And so I really felt like I'd come up against it in this particular instance, because nothing I was trying was working. So, but at the same time, I can tell you that when I started this whole machining phase of my life about 8 years ago or so, I didn't really know anything about it. And by preparing myself as well as I could in YouTube University, and also not being afraid to take chances and screw things up and redo it, I've been able to kind of stair-step my way up to some level of proficiency. You know, it's a process that never ends, and you never get to call yourself an expert because you're only just one step away from being humbled by the universe. I guess the point is, you see it a lot on YouTube channels, especially the ones that I watch, and certainly my channel as well, is intended to serve as examples of how you can bootstrap your performance, bootstrap your capability, your engineering, whatever it is you're trying to do, if you're a little less afraid to fail than most of us typically are. And I'm speaking about myself and other engineers, but I think a lot of people have the same thing. And in the end, you have to tell yourself that you're going to get more out of it, out of the experience, than the cost of the failure. I mean, honestly, if you're trying something that you've never done before, there's only so much preparing that you can do. At some point, you have to just do it. And it seems to me like I've heard "just do it" somewhere before. I've definitely heard "have a go," give it a crack, try and see. And in the end, I've come to realize that the worst thing that can happen is I have to do it over. And if I'm paying attention, I'll do it better than I did the first time. Sometimes I'll have to do it over 7 times. And I did say 7 because this story has a happy ending. But I'm going to take you through it a little bit just so you can understand. This was kind of a watershed event for me to figure out what was actually going on. And it wasn't anything earth-shattering, although it did shake the earth a little bit for a while. And I just wanted to share the story with you for whatever it's worth. I hope you find this interesting. I hope you find it useful. I guess, if anything, I'm just trying to inspire the thought that you should think more openly about the possibility of failure in what you're doing, and not be put off by it. not holding myself up as an example, because believe me, I was in a very black place after buggering up my 6th gear blank. But in the end, just sticking with it kind of paid off. So I'm in a better place now. Anyway, here's a little bit more of the story. Well, this is the machine as it exists now. But let's just talk a bit about the things that I looked for. I don't have a lot of video footage. I've got some that I'll sprinkle in here, but I don't have a lot because, you know, quite honestly, I wasn't in the right frame of mind for preserving events for posterity when I was in the middle of all this. And like I said, this was about a week of me trying every damn thing I could think of. But specifically, you know, the vibration was driven by the contact between the hob and the workpiece. That was clear. I could make it worse by taking a deeper cut, a harder cut. I could make it better by backing off, but I couldn't get rid of it altogether. I was always having a problem, and the onset of the problem was a sporadic, random, kind of chaotic, hard hit, where for some reason the cutting force went up for 2 or 3 teeth, and then it went back down again. And I couldn't figure that one out. So I started looking at movement of the knee, or the table gibs being loose, or the knee gib being loose. So I went through all that stuff and got everything set up as best I could. And that didn't work. I looked at the lash in the spindle assembly, and I didn't find anything, but I adjusted it, and that didn't work. I should point out that this is kind of an extreme case here. You've got a large diameter gear and 45-degree helix angle. And one of the implications of that from an engineering standpoint is normally when you're cutting a spur gear, the reaction to the cutting force, or the cutting force, is always in this direction. So this spindle is resisting an axial load. But when you're cutting on a 45-degree angle, the axial load goes down, but it's actually equal to the tangential load, which gets reacted as a torque on the system through the moment arm that's the radius of the gear. So you're putting a high torque load on the system as a result of the cutting force and the helix angle. And that load is impulsive because as the gear tooth passes over top dead center of the blank, that's where the cutting forces are highest. Then they dip off. And if you've noticed, the sound one of these machines makes when it's cutting is kind of like drum, 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 drum. That's the impulsive nature of the load. So I started looking at things that could cause that load to increase for starters. So I looked at the positioning of the workpiece and made sure everything was tied down, redid the center, redid the arbor, shortened up the connection, did all sorts of things there to try to deal with that. Then I started looking at the positioning of the spindle, and I discovered that the thrust washer had come out of adjustment, and I could move this spindle along its axis about 4 thousandths, 5 thousandths. So I took the column apart and readjusted that thrust to get it down to about a half a thou, which is acceptable. And none of that worked particularly well. I started looking at elements of the index train, and I finally centered in on the differential itself. Again, I didn't save a whole lot of video about this, but these axles that the spider gears are attached to were originally made of brass, and they were worn out. The spider gears were wobbly on their axis, and there's quite a bit of noise coming from that, but there's also the potential for some errors in the index signal that goes to the spindle. So I took that apart and I rebuilt that with steel axles and a impregnated bronze bushing. So those things ought to be quite a bit more robust. That didn't fix it either. I found an article online by a gear making professional, actually, that found that a friction brake on the work axis could reduce the level of torsional vibration and could result in better control of the dynamics of the system. Cool. So I built this. It's a piece of steel tube with a piece of cork gasket material as friction material there. This thing doesn't turn very fast, so it never generated any heat that I could tell. But I could adjust the lash with this setup here, which worked pretty well, actually. But that wasn't the problem. So when I started on my 7th gear, I started noticing the same kind of instability, the same kind of hard hits, and even one instance of just the beginnings of the kind of destructive vibration that I was afraid of. I was able to hit the E-stop quickly enough that I didn't scrap the blank. And I thought, well, let's figure out what's going on. So I put a dial indicator on the end of the overarm against the table. And I started up the machine and I just looked at it, and I was getting about a normal variation of about a thou. But then when one of those hard hits took place, it would go up to 5 or 6 thou. That's a lot for a machine. Just to calibrate it, I set it up and I put my entire weight on the end of that thing, and I could only make it move about 4/10. So something was causing sporadic and chaotic high loads. And I thought, well, I'm not sure this is going to do it, but let's build an outboard brace. Now, when this machine was new, it would have come with a cast iron brace as part of its complement of equipment. Mine is functionally similar to that. There's a clampy deal at the bottom that clamps it to the dovetail of the knee, and then this is all made out of fabricated 1/2-inch steel and tied to the outboard arbor support. And that's pretty rigid. I couldn't get any deflection at all using the same test load. That didn't work either. I was still having problems, and I was only able to take maybe a 20 thou deep pass, and that's just not where I want to be with this machine. So I let the machine run, and I was just looking at it, and I was looking for problems in the feed system, anything in this business back here. This is the feed gear train at the back that drives the lead screw for the table. And I just happened to have my hand on that gear right there when the machine had one of those hard hits. And I felt that gear jump like this. And I thought, what could cause that? And when I started looking around, what I realized was that the feed screw was sticking. And it was sticking because I had put too much load on the end play control, which is this nut right there. That's the stupidest thing. This is not a very good design. Again, this is OEM stuff. It's not my design, but in the process of using this screw to put kind of bearing to bearing preload in the shaft, I got it too tight and it was sticking. And so what was happening was the feed screw or the feed system was winding up. It was taking up all the backlash plus all the elastic deformation, all the spindles and axles and whatever can deflect was deflecting, building up load until there was enough load to get it to pop free. And when it popped free, it was feeding that way, and it was feeding the workpiece into the hob at some rate that was not controlled. And that's what was causing the random hard hits. It all makes perfectly good sense when I sit down and think about it. Well, I promised you a happy ending. This is the gear I made yesterday. It's 43 teeth, 45 degrees, and it's not perfect, but it's good enough. And this is how the system is going to look when I get this together. This is going to bring the index signal into the analog brain of the new hobbing machine. So that's the story. It's a little sad how trivial the final answer seemed to be, but there you go. It was quite an experience. I stand before you a sadder but wiser engineer. On the other hand, I got a chance to make a lot of stuff for the machine, and all that's good, clean fun. And came with its own mistakes and its own learning opportunities. Every project I do, I'll learn 1,000 new things, mainly by screwing up. So if you want a tagline to remember this video by, maybe it's this. Unless you're trying to rescue Apollo astronauts, failure is an option. In fact, failure can be your friend if you think about it in the right way. Anyway, that's all for now. See you next time.